My talk today is called Reasonable JavaScript, and I know I'm sitting between you and dinner and drinks, so I hope you can give me 45 minutes of your time to get through this, and hopefully you walk away with something. What does it mean for code to be easy to reason about? Like, I've heard it at many conferences, I've heard it at meetups, I've heard just people randomly say easy to reason about when they talk about some code or some concept. Like, they might say, React makes code easy to reason about, or one-way data flow makes code easy to reason about, or like static type checking makes code easy to reason about, or immutability makes code easy to reason about, pure functions make code easy to reason about. And before you know it, you hear it everywhere in so many different contexts, and I didn't really know what it meant. And I kind of wanted to create a concrete definition, or somewhat of a concrete definition for what this means and why we talk about reasoning about code. So that's kind of what my talk is going to be about today. And so the goals are, what makes code easy to reason about? So define what makes code easy to reason about. Why JavaScript sometimes makes it hard to write code that's easy to reason about. And then lastly, talk about different methodologies that we can use to write JavaScript code that's easy to reason about. If you walk away with anything in this talk, I want you to walk away with knowing what it actually means to reason about code and not hand wave over this concept. Before getting started, someone keep track of how many times I say easy to reason about, because it's going to be a lot. OK, so let's get started. I'm going to start off by saying that JavaScript is a fantastic language for many reasons. I mean, you're all here today. You probably use JavaScript every day. We're crazy enough to use it on our servers as well. So why is JavaScript awesome? Well, for one, it runs everywhere, right? It's on every browser, every operating system, every device. It's incredibly everywhere. Second, it's really versatile. Like, we can use it for a lot of different things. We can use it as a simple scripting language. We can use it to build complex web applications. We can use it to build sophisticated APIs, bots, IoT apps, desktop apps, and now even native mobile applications. So it's sort of everywhere. Immediate feedback loop. I think this is really incredibly important, especially for beginners. Like, creators need to see what they're making immediately, and I think JavaScript, HTML, CSS gives you that. Most other languages don't give you that as much, so that's really important. Also, the community. I mean, you guys are all here today. It's an awesome community. I love being part of the JavaScript community, and that's one of the reasons I fell in love with programming, and I think the community around JavaScript is just incredible. And lastly, it's beginner friendly, and the reason I say it's beginner friendly is because there's no compilation, no complex developer environments. All you really need is a text editor and a browser. No type system that you have to learn as a beginner. Global support in any browser, and as I said before, immediate feedback loop. But I would say this is a blessing and a curse, because I think the same characteristics that make JavaScript easy to learn and great for beginners are also the same thing that make it difficult to write code that's easy to reason about. And so I'm going to start off with an example and kind of show you what I mean by that. We're going to have this calculate area function, and you're going to see this a lot throughout the presentation, so I hope you get used to it. And all it does is it takes a bunch of radii, and it iterates over them, and calculates the area, and returns the areas of these radii. Now, as good programmers that we are, let's understand the program's behavior. Let's actually figure this out, if it works, right? First question we might ask is, does it function? Right, so we might just pass a bunch of radii and check that the output looks correct. And to me, that looks fine, so we can just say, yeah, it functions. It looks good so far. The next question we might ask is, does it do anything that we don't want it to do? Like, we tested that it works, but what if you log the original array of radii? We see that it got mutated. It's now the areas and no longer the radii. That's not good. What if we want the radii to calculate the diameter later, or the circumference, whatever it is? So we're mutating our original array. Next question we might ask is it consistent in its behavior? So here we pass in a bunch of radii, we get an output, Then some time passes, and later on in your program, some evil programmer checks in some code that updates your pi variable, and then now your areas are totally janky and off. That's not very good, right? Another question you might ask is, does it properly handle all possible inputs? So what if radii, for some reason, ends up being undefined? What ends up happening in JavaScript is it throws an exception, a type error, and says you can't calculate length on undefined. OK, so then you being the good programmer that you are, you're like, OK, let me go back and fix this. Let's redesign our program. So step one, let's not mutate the original array. So what we're going to do instead is create a new array called the result and put the areas in that result array and return the result array. Another thing we're going to do is remove the global dependencies. So the pi was global, and so anyone could mutate it. So we move it into our function and put it in the scope of the function so that no one can touch our pi. Step three, handle invalid input arguments. So we're going to do some error checking before we actually iterate over that array of radii. We're going to say if it's undefined or null, throw an error. If it's not an array, throw an error. And then we actually do our logic. So now let's go back and understand our improved program's behavior, right? Does it work? Yeah, it works. Does it mutate the original radii? No. Does it return consistent results over time? Yeah, it seems to. And does it handle invalid inputs? Yeah, it seems to do that too. Looking good. But I'm going to do some more battle testing because I thought of another edge case. What if we pass in undefined instead of a number into an array? Because in JavaScript, undefined squared is nan, we get nan, and it silently fails and returns you that array. Similarly, if you pass in a string, you get 0, because string squared apparently is 0, which is awesome, right? So then you cry, and you go back, and you redesign your program again, and you test for this edge case where you actually check that each of the radii being passed in is a number. If it's not, they're an error. Otherwise, actually calculate the result. Now, I think we have a winner where it correctly handles all those edge cases. So what did we learn? One, reliance on global variables causes our programs to be unreliable. I think this is a no-brainer. Everyone knows this already. But we just learned that through our calculate area function. Second, mutable data can lead to unintended side effects. Because we were able to mutate the radii, we did mutate it. We didn't have a restriction around it, so we did. Having no way to restrict the type of data that can be passed into a function makes us think extra hard about error handling. Because in JavaScript we don't have types, we can pass in anything, and so we have to do extra error handling in the function. And type coercion, like undefined squared being nan or string squared being 0, makes it hard to predict the behavior of our code. And realistically, if you look at this, our finished version of the program, like, is this something a beginner would really write? Like, I don't know, if this was me a year ago, I probably wouldn't have thought of all these edge cases and written a function like this. I would have written just the original one, because these are not things I'm really thinking about. I'm just thinking about getting a function to work. And so this is why some people get frustrated with JavaScript. There's like no compile time restrictions. It allows you to do a lot, but you will do anything. So one possible conclusion is you can't write code that's easy to reason about in JavaScript. So then we give up. Definitely not, right? I'm here for the same reason you are, and we all love JavaScript. So my proposed conclusion is, with a little bit of extra effort, you can write reasonable JavaScript. So for the rest of this talk, I'm going to talk about a few of many building blocks that we can use to write reasonable JavaScript. And before getting started, I want to create a definition for how we can think about reasoning out, or like what makes code easy to reason about, so that we can go back after each building block and see which one of these criteria that building block meets. So I'm going to say when a program does not affect or mutate external state, it's easy to reason about. And it should not also rely on external state. And it should always return the same corresponding output for a given input. And we'll see why these three characteristics leads to code that's easier to understand the intent of, easier to reuse, easier to maintain, easier to refactor, easier to test, and hence easier to reason about. Okay, let's begin. First building block is unit tests. So we have our function, right? Original function. And we might write a test that says, this should work. And you pass in an array of radii, and you expect your expected results, and you test that it equals your expected result, and that passes. And if you're a good test writer, you might also write a test that says, this should not work, and you pass in invalid inputs. In this case, you expect that function to throw an error, but this test fails. It doesn't throw an error, because we saw that undefined squared equals nan, and it'll not throw. So then you might go back, update your program so that your test pass, and now your test pass. So if you go back to our 3 bullet points, how do tests help? Do they help us not affect or mutate external state? Not really. Do they help us ensure that we do not rely on external state? Not really. But do they help us ensure that they're always returning the same corresponding output for a given input? Yeah, we can test for that, because we can always test. If we have a test that something should return something, we can guarantee that it will always return that. So overall, why tests, right? There's a lot of benefits to writing tests. We can verify that our code behaves correctly. We can test error cases and edge cases. It's like living documentation, essentially. And we can make changes without fear, because if your tests fail, then you just update you know that something went wrong. So second building block is types. Types are not native to JavaScript, so I'm going to give a definition, because I know most people might not be using types yet. So a type is just a classification of data which tells the compiler or interpreter how the programmer intends to use the data. Essentially, it just defines a set of inputs and outputs to a function. So I'm going to use a library called Flow, which was released by Facebook, and it's an API that allows you to add types to JavaScript. You can also use something like TypeScript. I chose Flow because it's just easier to, I find, I use it myself. I haven't used TypeScript, but, sorry, I haven't used TypeScript. So I'm going to add types to our original program. And you'll see I added a type of pi as number. And then I added to our input argument radii, I said that's an array of numbers. And then the output is also an array of numbers. Now, if we had a function that properly passes in an array of radii, and when you flow check it, it'll say found 0 errors. But if you had somewhere in your code, if someone passed a string into this function and you type checked it, Flow would complain, and Flow would say, string, this type is incompatible with array number. So it catches this stuff for you at compile time before you ship it to your customers while you're coding, so that you can fix it and deploy correct code. So why types? I want to explain a few different reasons. One, it separates data from behavior. So when you're writing types, it forces you to think about what your data is before you think about what the actual behavior is. And this kind of mental separation helps a lot when you're coding. So that's our data, and then this is our behavior. Two, it serves as living documentation. I actually pulled this right out of our code base. So we have this function called generate params. It takes apparently a quote, a commit, and an amount, and it does some business logic and returns a params object. When I looked at this, I was like, what do I pass to this function? What's quote? Is that a string? Is that a number? Is that a Boolean? Like, I had no idea how to use this function, so then I had to ask around, and then, or like grep through my code base and figure out what's being passed into this. And then I updated it so that I added documentation on top saying, okay, this is a Boolean, this is a Boolean, this is a string. This is great and all, but comments go out of date and documentation goes out of date. I know I see so many comments in my code base which are totally out of date or just terrible documentation. It's not consistent. So with types, what happens is your documentation is in your code. And anytime you update the function, you have to update the type, so the documentation automatically gets updated. So here we say quote Boolean, commit Boolean, amount number, and then we say it returns an object. So another reason is it removes convoluted error handling and testing. So this is our flow, our function with that's type checked, right? So we told it that it's going to take an array of numbers and return an array of numbers. Sorry. And because of this, we don't have to do all the error handling that we did before. Because even if you tried to pass in a string or some invalid input, it'll automatically throw at compile time. So now our program becomes actually what we would have written without all the error handling. Another reason is it eliminates an entire category of bugs. So the number one bug that we see in our React or like front-end code base is type errors. And a static type checker would eliminate that. So I'm going to show you a very basic example of how this is how a type checker could help. So let's say you have some app state and there's an is fetching, it's is fetching or not, and then there's a simple array of messages, and then you fetch your data, and then you have a component that takes your app state and it just says you have messages.length unread messages, and then it maps over the message and displays the message. Super simple component. But what if your API is unreliable and it returns undefined or null or something? Then you have a typer in your bug snag that says typer cannot read property of a length of undefined. But if we were to use a type checker like Flow, we can add types. We can say our app state is fetching is a Boolean, and I'm going to say messages. Because I know my API is unreliable, I'm going to say messages is a maybe an array of strings. That maybe means it can either be an array of strings or null and undefined. Fetch the data, the same component. Now, if you try to flow check this, what Flow will say is property cannot be accessed on possibly null value. So it's saying because your messages array can be possibly null, you can't do .length on it. Handle that, programmer. So then you go back and you're like, okay, I'll handle that. And now you're reminded to say, okay, if it is fetching, display something else, or if the message is null or undefined, display a message saying that it failed, and if it actually exists, then actually display the component that you wanted. So all this is happening at compile time, and the compiler is telling you how to fix your mistakes before it gets shipped. So you can define your program invariants and let the compiler tell you when something goes wrong. And then Flow will say 0 errors, and you can do your happy dance. Okay, other benefits of types, earlier detection of mistakes, as we just saw. If the satisfaction of like if it compiles, it runs, can refactor with greater confidence, because if you update a type and you see compile errors, you know exactly where the code is being used incorrectly. And it serves as a domain modeling tool, where like you saw a simple example with the app state, you can expand that and like actually model your entire app domain using types, which is really helpful for documentation. Okay, so going back to our checklist, how do types help? Well, do they ensure that we do not affect or mutate external state? Not really. Do they ensure that we do not rely on external state? Not really. Do they ensure that they always return the same corresponding output for a given input? I'm going to give this a maybe, because they do ensure that the function always returns the same type. So if you say array of numbers, it'll always return an array of numbers, but it doesn't ensure that it always returns the same data, per se. So I'm going to give this a maybe. But we both saw that tests and types give us a lot of benefits, and they don't really fit into this like model, these 3 bullet points. So I'm going to propose that we add another bullet point to our reasoning about what it means to reason about code. I'm going to say when the code is guaranteed to work as intended by the programmer. Because that's what tests and types do, essentially. They guarantee that the program works as intended by the programmer. So this is our updated list. OK, so third building block, immutable data. So Lee Byron gave an amazing talk about this earlier today. So I don't think I have to explain the concept as much. But basically, immutable data is when state cannot change after it's created. If you want to change the immutable object, you don't. What you do instead is you create a new object with a changed value and point your reference to it. So example, here's me today. And then I have a me a year from now. And I just increment my age by 1. And if I check that they're the same, it returns true. So this is not immutable because we're updating the object. But if we were to use an immutable object, I'm using immutable.js. We create an immutable record, and then when we want to update it, it creates a new object. So we're setting the age to what my age is today plus 1. And we check that it's equal. It's not because it's a new object. That's immutable. So going back to our area function, let's use immutable data instead of immutable data. And because we're using immutable data, we're forced to map over it and return a new array. So here we're just mapping over the input radii and calculating the area. And now if we check that the original radii equals the new areas, it doesn't. So now our data is immutable. And you're probably like, OK, so why would I care about this, right? All right, I'm going to try to convince you with another example. Who's gotten this in an interview question? Oh, OK, this makes me cringe. So this is quicksort. I've gotten it a billion times in an interview question. And it's like the most, it makes sense logically, but the most confusing thing to implement. Like you started at a pivot point, and then for each value lower than the pivot, you increment the pivot by 1 and put the value to the left of the current pivot, and you keep doing this recursively until you get a sorted array. But let's say we were in an interview, and we accidentally make this tiny mistake where we put this J++ down here instead of at the top of the if block. Then when we go to show the code to the interviewer, we get this. So then we might put a debugger and try to figure out where stuff is going wrong, and then go fix the program to match our intent. But we probably won't get the job. But what if I told you that with immutable data, our function could look like this? Each time, because we can't mutate the values, each time what we do is we first get the pivot, which is the first item in the list, then get the rest of the items in the array, calculate a new reference to all the items less than the pivot, calculate a reference to all the items greater than the pivot, and you're simply, at each time, concatenating all the items less than the pivot to the pivot, and the greater than the pivot to the pivot. And because you're not having to deal with sequence of operations, for loops, while loops, it becomes a lot more declarative. Like when you read this, it looks like you're just describing what quicksort is. You're not actually telling it how to do the quicksort. And now when you do the quicksort on this, you get the correct answer, and so you get the job. A lot of people might say, wow, it's a lot of objects, especially if your array is massive. And my favorite quote, one of my favorite quotes by someone I look up to, Wes Dyer, is he says, make it correct, make it clear, make it concise, make it fast, in that order. Like, I don't think, unless performance really, really matters, I'd rather have code that looks like declarative and looks like the second example than the first one. So overall, why immutable data? Because when data doesn't change, we can just use the data and not think about whether making changes is safe. No one can mess with your data, nor you theirs. So if we go back to our checklist, what does immutable data give us? Does it ensure that we don't affect or mutate external state? Yeah, that's the definition of immutable data. Does it ensure that we don't rely on external state? Not really. Does it ensure that it always returns the same corresponding output for a given input? Not really. Does it ensure that it's guaranteed to work as intended by the programmer? I'm going to say yes, because we're not mutating stuff, and so there's a higher guarantee of things working as intended. Other reasons, things like temporal coupling, persistence, lazy operations, these are things I'm not going to go into, but worth digging into if you're interested about immutable data. Okay, so next building block, pure functions. Definition. So I'm going to start off with what is not a pure function. When something relies on some external state that's not explicitly passed to it as an argument. So what is a pure function? A function that relies only on parameters that are explicitly passed to it as arguments to produce a result. So example, here we have a self-executing function. I'm going to pull out and just pass in 1. I'm going to say C equals and pass in 1. And what C is a function now that takes in B and returns A. And A is bound to 1 because I passed in 1 up there. Now, if we take C and pass in anything, it'll always return 1. And that's because of the closure variable, the magic of closures, right? And this is not pure, because if you look at the function B returning A, you can't tell just by looking at it what it'll return without understanding the magic of the free variable A. So this is not pure. Similarly, let's say we have some function that just simply tells you if some amount exceeds the buy limit of your customer. So then you first fetch the limit for the customer asynchronously, and then you say if the amount is greater than the limit, return true, otherwise false. This is not pure either because it relies on some external state. Simple enough, right? When something relies on external state like this, the one thing that becomes really, really hard is testing. So to test that function, we have to now go find a mocking library, mock out the response from the API, and then test it, which is a pain in the butt, we all know. But if we were to purify this, we're going to assume this function somehow knows the limit. And then you can program in like a higher level. You can say, simply, if the amount is greater than the limit, return true, otherwise return false. And now testing becomes so much easier. So going back to our checklist, does a pure function ensure that we do not affect or mutate external state? No. But does it ensure that we don't rely on external state? Yes. Does it always return the same corresponding output for a given input? Yes, because it's never relying on external state, so it should always return the same output. Is it guaranteed to work as intended by the programmer? Yes, because a pure function, you can look at exactly what it is, and you don't need to look at anything external. But there's more. When you combine the previous two concepts of pure function and immutability, what you get is something called referential transparency. And this is simply means the ability to freely replace an expression with its value and not change the behavior of the program. So anytime you see a function, you can actually replace it by the return value, and it'll always be the same, and your program should work the same. And why does it matter? Because if you go back to our checklist, when you have referential transparency, which means pure functions and immutability, what you get is all 4. So I can end my presentation here, but I want to talk about one more building block because I think it's pretty important, and JavaScript is particularly good at letting us use this building block. Taking advantage of functions as first-class entities. So what does it mean for a function to be a first-class entity, right? It just means we can refer to them as constants and variables. We can pass them as parameters to other functions. We can return them as results from other functions. So functions, you can think of them as variables and pass them around, do whatever you want with it. So why use them? Let's take a look. I'm going to talk about 4 different ways that we can use them. There's so many different ways that you can use functions as first-class citizens, but we won't have time for all of them. So suggestion 1 is replace loops with higher-order functions like map, filter, etc. So an example, going back to our original function, if we just I'm using a library called Ramda. So anytime you see r dot something, it's a library called Ramda, which is a JavaScript utility library for, like similar to Lodash, but it's functional. And I'm just replacing this for loop with a map. And it automatically makes it so much smaller and simpler. And if you're like, that's not a big deal, I'll try to show you another example and convince you. So we have this function, sum of odd squares less than 10,000. And you need to sum all of the odd squares less than 10,000. So you have an array of odd squares. And first, you determine what all the odd squares are that are less than 10,000. So you have a while loop and find all the odd squares and push them into that array. And then you iterate through that array of odd squares and sum them up. This is one way of doing it. And you get 166, 650. If we were to use higher order functions, we can break this up like this. We can say, let's have a simple function that just tells me if x is less than 10,000. Let's have another function that tells me if x is odd. Let's have another function that tells me if how to square x. And then I'm just going to tell it what to do and not how to do it. So I'm going to say, first, map over my array and square the items. Then I'm going to take all of the ones that are less than 10,000, filter for the odd ones, and sum them. And I get the same thing. So here, I'm telling it what to do, whereas before, I was telling it how to do it. And it becomes so much more declarative. So if you go back to our checklist, what do higher order functions give us? Do they ensure that we don't affect or mutate external state? Not always, but like things like map and filter, they'll usually return a new array, but it's not always guaranteed. So I'm going to give that a maybe. Do they ensure that we don't rely on external state? Not really. Do they ensure that we always return the same corresponding output for a given input? Not really. Do they guarantee that to work as intended by a programmer? Not really. But they do give us a lot of other benefits, like things are shorter and less clunky. They're easier to read, more descriptive, allows us to define computations by what we want instead of how we want it. Overall, when you use higher order functions, it's more information and less noise. Another way to use functions as first-class citizens is parameterizing as much as you can. So going back to our calculate area function, let's say later on we want to have a calculate diameter function. That's the same thing, but the computation in the for loop is a little bit different. It just multiplies the radius by 2. Let's parameterize this, right? Let's parameterize our action by extracting out the common code and parameterizing it. So I'm going to say, here's how you calculate an area, and here's how you calculate diameter. Except my function is wrong. Just pretend that this is radius times 2 for calculate diameter. And then I'm going to have a generic function that simply takes an action and a list and maps over that list and performs the action on each item. Now I can pass in my calculate area function, calculate diameter function with any into my generic action on list function. Now I can use generic functions everywhere. Let's say I can have a square function, a double function, a negate function, and I can use the same action on list generic function to pass in the action and any list. And so what we end up having is very generic functions instead of specialized functions to do everything. So going back to our checklist, does parameterizing stuff ensure that we don't affect or mutate external state? Not really. Does it ensure that we don't rely on external state? Not really. Does it ensure that we always return the same corresponding output for a given input? Not really. Does it guarantee to work as intended by the programmer? Not really. But it does give us a lot of other benefits, like passing any list to any data, and basically having like a generalized function, and decoupling the behavior from the data, like our action from the list. Suggestion 3, partial application. So first, the definition. Partial application means we can turn a function that expects multiple parameters into one that will keep returning a new function until it receives all its arguments. This is a mouthful and hard to kind of picture until you probably see an example. So I'm going to jump right into an example. I have a simple function that applies fees. It takes a fee and an amount, and it just applies the fee to the amount and returns a new amount. This is a regular non-partial application function, and when we want to use it, we have to pass in a fee and an amount. If we try to just pass in the fee, as in the last example here, it'll return nan, because when you don't pass in all the parameters in JavaScript, it'll return nan. But if we were to use partial application, I'm again using Lambda, I can partially apply the fee. So let's say I have different types of fees. Like at Coinbase, you have all different types of fees. And so I have one function that uses my apply fees function to create an apply bank fee function. And it uses the same function to create a credit card fee function, and uses the same function to create a PayPal fee function. And now I have these functions that are partially applied, and when I use them, I just pass in the amount. I don't have to worry about passing in the fee. I just pass in the amount, and I get the different amounts based on what my fee is. So what? All right, so I'm going to show you another example to see if you might be convinced. Here's an old piece of code that I found in a code base that I updated, but this was how it looked. Basically, what it does is it fetches the valid payment methods for a user. And what valid means is first it fetches all the payment methods for the user, then it iterates through the payment methods and finds the ones that have allow by true as a property, and then it iterates through them again and checks that a property limits.by.remaining is greater than 0, so meaning their by limit is greater than 0. And then it just formats it by returning just an ID and the name of the payment method. Now, if you use our own advice and use high-order functions, we can clean it up to look like this. We can just filter for the ones that allow by, then filter for the ones where limit.by.remaining is greater than 0, and then just return the ID and the name. So that looks way better already. But what if I told you that if we use partial applications, it can look like this? Essentially, each time you're passing in a function that expects data at the very end. You're never dealing with the data itself. The data is always coming last. Instead, you're just dealing with what you want to do with it. You're saying, first, I want to pick the data property off the response. Then I want to filter for the ones where the property allowed by is true. Then I want to filter for the ones where limit.by.remaining is greater than 0. Then I want to pick the ID and the name property off those objects. So in this case, because I'm simply telling it what to do, I'm never introducing the data, it just becomes so much smaller and cleaner and more expressive. So going back to our checklist, does partial application ensure that we don't affect or mutate external state? Not really. Does it ensure that we don't rely on external state? Not really. Does it ensure that we always return the same corresponding output for a given input? Not really. Is it guaranteed to work as intended by a programmer? Not really. But there's obviously a lot of benefits, like you saw. Number one is readability. Number two, it's a powerful way of transforming your data in a functional way. Third, we can use functions as generic building blocks that work with different kinds of data, because you're never dealing with the data. The data always comes last. And dependency injection. Like with the fee example, I pass in the fee as a dependency, and I can now use generic functions with the fee passed in. All right, last building block, I promise. Use composition. This is another way we can use functions as first-class citizens. So we saw in all the previous examples how we're kind of throwing functions around, we're passing them as parameters, returning them as our return values. So once we get used to this idea of passing functions to other functions, we can start to discover ways to combine two or more functions together. And this is what composition is. So start with an example. This function just takes an amount and it applies tax and shipping and handling. And it just applies the tax and shipping and handling and returns you the amount. With composition, I can break this up into apply tax and then apply shipping and handling. They're two separate functions, and I compose them. So I'm doing lambda.compose, and how compose works is it works backwards from left to right. So first it'll apply tax to the data I passed in, then it'll apply shipping and handling to the data I passed in. Let's say later we want to add a gratefulness surcharge, because I live in San Francisco and people find reasons to tax you on the most ridiculous things and surcharge you on the most ridiculous things. Like I got a cleanliness tax once at a restaurant, which was awesome. So let's say we have an applied tax and shipping and handling and gratefulness surcharge function. So we might just add our gratefulness surcharge and get back that. Or if we were to use composition, we can create a simple apply gratefulness surcharge function and just pop it onto our compose stack like that. And then later, let's say we don't want to add this surcharge, we can also create a separate function that doesn't apply that charge. Later, we want to add a 5% discount. So we can either apply tax and shipping and handling and gratefulness surcharge and discount, or we can use composition and apply our discount and pop it onto our compose stack. I think you're starting to get the point, but in case you don't, let's say we want to also format money. I'm not even going to go into the regular example. I'm just going to go into the composition example. But we just create a function that formats money and then pop it onto our compose stack. And we get our formatted amount. So why composition? Each function becomes useful on its own. We can easily create fresh new functionality from existing functions. We can break apart pieces of behavior and test them independently. We can test each of those functions independently and easily because they're so much more simpler. And it declutters code, so readability again. So going to our checklist, does composition ensure we don't affect or mutate external state? Not really. Does it ensure we don't rely on external state? Not really. Does it ensure that we always return the same corresponding output for a given input? Not really. Does it ensure that we're guaranteed to work? Does it ensure that it's guaranteed to work as intended by a programmer? Not really. So we saw that like with first-class functions, it's a little bit weird. They didn't really meet any of our criteria for reasoning about code necessarily. So, but they did give us a lot of advantages, right? Like when you start to take advantage of functions as first-class citizens, it encourages us to use functions as the primary unit of abstraction. Like small, independent, composable functions become the tool we use to model and solve any problem. And we saw all the benefits of doing that. So I'm going to propose that we add one last bullet to our list of what it means to reason about code. I'm going to say, when code is modular and generic, it enables us to reason about code better. And that's what functions as first-class citizens gives us. It creates modular and generic code. So when you have all these, what you get is code that's easier to understand the intent of, easier to reuse, easier to maintain, easier to refactor, easier to test, and easier to reason about. So recap, we talked about tests, types, immutable data, pure functions, functions as first-class entities, and within that, we talked about higher-order functions over loops, parameterizing as much as you can, composition, and partial application. So I'm not going to leave without putting it all together in one, of course. So here, I'm going to go back to our calculate area function and use basically everything I just talked about. You don't have to go this extreme, obviously. I'm not saying you have to adopt every one of these things. I'm just showing you what it looks like if you wanted to. I'm importing a list from immutable.js and map and pipe from Lambda. I'm using flow, as you can see. So I have my pi defined as a number. Then I'm creating a type of action, and this type of action takes in a value, which is of type number, and returns a number. And I'm creating a calculate area function that is of type action, that takes radius, which is a number, and returns the area, which is a number, which is what I define the action type to be. And then I have a generic doStuffOnList function that takes a list, which is of type list number, which is a list of numbers, and takes an action, which is of type action that I defined up there, and then it returns a list of numbers. I'm just mapping over that list and performing the action on it. And then I have my radii, which is an immutable list. And then I do stuff on the list. I pass in the radii and the calculate area function, and I get my list. I haven't mutated anything. The couple of things I missed in here are composition, so I'm going to put that in here too. So I have another function, format, which is also of type action, similar to our calculate area action. It takes a radius and it formats it, so it truncates all the decimals, extra decimals. And I'm going to pipe. Pipe is opposite of compose, so it just does right to left, left to right. So I'm going to first map over my array and calculate the area, then map over it and format it. And then what I end up getting is a formatted list. So everything in one. So I don't think we need to go to this extreme of obviously using everything I talked about. I think the point of it is that you can kind of pick and choose in JavaScript what you want to use. Like if type errors are a huge thing in your code base, maybe introduce static type checking. That might help. Or if you're finding that it's really hard to maintain large state, maybe using immutable data might help, like Lee Byron said. Or if you're finding that you are having a hard time testing functions, maybe think about using more pure functions. Like, figure out what your problem is and solve for that. You don't need to use everything, but what's amazing about JavaScript is we have all these tools that we can use to write better JavaScript. So putting it all together, JavaScript strives to be an incredibly dynamic and flexible language. This sometimes puts the burden on a programmer to consciously write good code. And it makes it easy for someone to bash on JavaScript for its dynamic typing, aggressive type coercion, mutable data structures, and whatever you want to bash on JavaScript for. But just remember that JavaScript wouldn't be where it is today if it weren't this flexible and if it weren't this dynamic. Its incredible flexibility and forgiving nature is exactly what gets beginners in the door and enables it to be used for everything that it is used for. And we're fortunate enough that there are tools and methodologies that enable us to write good JavaScript code. So I call this a win-win situation. So let's go write some code that's easy to reason about.